And Susan, very quickly, just tell me when you want to upload the slides, and I'll quickly do it.
Thank you.
Okay, welcome everybody. Thank you so much for joining us at another of the International Guidance Counsellor Conference sessions. This is the STEM field mock interview. So it's a really wonderful opportunity to get a better insight into the interview process that we operate as part of the Cambridge admissions process. So for those of you who haven't seen me, although I have been around in the conference, so probably a familiar face for many of you by this point, but I'm Amy, I'm a member of the international team, and I'll just be facilitating the session. The main kind of portion of the session will be kind of an introduction and then example interview that my colleagues Susan and Guy will be kindly doing for us, and then there will be an opportunity to ask questions at the end of the session. So do kind of be thinking about any questions you have as we go through, and there is the function to ask those on the sidebar there, and there is a function to ask them anonymously as well if you want to do that. So we have 45 minutes for the session, so we will jump straight in. The session will be recorded and available to view after. We've also got an arts and humanities example that took place earlier today that you might find interesting to watch at another point to kind of compare and contrast the two kind of subject areas. So thank you so much for joining us. Thank you for Susan and Guy for taking us through this. I will now kind of pass over to them to introduce themselves and then make a start with a brief introduction and then jumping straight into the mock interview. Thanks both.
Thank you. So my name is Susan Haynes. I am the admissions tutor at Queen's College, and I cover all subjects at Queen's College, but I am a physicist by training. I studied natural sciences in Cambridge and then specialised in physics. And Guy is a current student at Queen's, and I'll just pass over to him to introduce himself.
Hello, I'm Guy. I am a second year student at Queen's, currently in the natural sciences tripos, and I'm currently studying physics and maths.
Thank you, Guy. So if it's possible to just share my slides again. And while those are coming up, brilliant, thank you. So I thought it would just be helpful to have a couple of slides here, just to explain a bit of the background to what we're trying to do in STEM interviews. I know that many of you will have already got quite a good idea about what the interview process involves, but STEM interviews are slightly different from arts and humanities interviews. So if I flick over. So for STEM interviews, often an applicant will have two interviews and they will predominantly be subject related. They may have one interview if that interview is a bit longer. And during the interviews, what we're really trying to do is test several different areas of the applicant's knowledge and understanding of science. So it will mostly be problem solving. And in each interview, they'll be asked maybe two or three different questions covering a range of different topics. That might be for a natural sciences applicant, for example, given Guy's background and my background, a physics question, a maths question, a chemistry question, and then maybe another maths question across the two interviews. And the idea is to really give the applicants an opportunity to show us their strengths and abilities across a range of different subject areas. The questions that they're asked do tend to be science problems. They will be based, we hope, on things that they've already met at school, or we'll give them some extra information if they might need that. But we're asking them to apply that knowledge to a new scenario and to test out how they think and how they approach a problem, and get to hopefully the correct answer in an analytical and logical way. And usually the questions are also staged. Hopefully you'll see that with the mock interview I'm about to do with Guy, but they build in difficulty. But throughout the question, there will always be support, and the applicant is always talking with the interviewers and discussing their thought process so that we can assist them if they get stuck. There may not be very much discussion of things that your applicants have written in their personal statement, for example. There might be a little bit, but it does tend to focus more on the problem solving. And if you have an applicant for medicine or veterinary medicine, there will be some discussion of vocational aspects. So their reflections on what it might be like to work as a doctor, for example, or any work experience that they've done. So what you're going to see from me and from Guy today is, because of our backgrounds, quite physicsy, mathsy type question. Obviously, if you had an applicant that was applying for biological sciences, the questions might be more biological in nature. For computer science, they might be a bit more mathematical and so on. So simply because of my background and Guy's background, you will see a certain set of questions today, but I hope it will illustrate to you the kinds of approaches we take. One other thing that I would like to just add, and if you're watching the recording, you will have time to go away and look up these resources. We're really often asked how you can help your students to prepare for STEM interviews. The key thing is getting them to revise the content that they'll already have met at school. Another thing is to get them to talk about any experiences they may have. That's probably most relevant for medics and vet medicine applicants. Getting them to actually engage with material and explore material beyond their school curriculum is really important as well. And there's a set of resources listed here, which are all related to the University of Cambridge, but give them the opportunity to practice some problem solving, which is also a really key thing that they should do to prepare. And finally, particularly in the STEM subjects, sometimes students don't feel all that comfortable talking through their problem solving as they're doing it. So getting them used to doing that is a really important thing to do, getting them used to asking for clarification or for extra information if they need it, and if they get stuck at any point. Quite often, students are used to sitting and solving a problem on their own, and they're not really verbally addressing their thought process. But if they don't do that, it can be quite difficult for the interviewers to provide assistance and to provide guidance when they need it. So we really recommend that they get used to practicing doing this ahead of any interview. Okay, having said all of that, Guy, we're going to move on. Okay, so I just need to share a different screen, if you bear with me. So, Guy, I'm not sure in your interviews if you had an online interview. Is that right?
I did actually, yeah.
Did, yeah. Okay, so what we are doing today for the attendees is something a bit close to an online interview. And in a STEM interview, quite often we would have some kind of shared whiteboard or shared screen that we would use to discuss the problems with the applicant. So Guy and I are mimicking that today with this shared whiteboard screen. And Guy, you have no idea what I'm about to ask you. So what I'm going to ask you to do is an estimation question. And I'm going to ask you to estimate the number of table tennis balls that you could fit in a car.
Oh, okay.
Okay.
Sure.
Now, first of all, I don't necessarily expect you to know what a table tennis ball looks like. Yeah, is that fair? Okay.
I'm quite familiar with table tennis balls.
Do you know how big they might be, though? Because you need that piece of information.
Well,
I'm just going to put that up for you. Hold on.
Good estimate.
I'm going to make it easier for you. Here you go.
I see. Very nice. So if we're trying to fit as many balls into a car as we can, this is very much about the volume and volume ratio of the table tennis ball to the car. We can see from that picture, therefore, that the diameter of the ball is about 4 centimeters. That gives a radius. I might write a little bit.
Write it down, yeah.
That gives a radius of half of that, which would be 2 centimeters.
Yep.
I think it would probably be helpful to put it into standard form, just so we have sort of consistency with units. So then the volume of a sphere is given by the formula. Oops, sorry, press the button on my pen. There we go. So I'll try again. Is given by 4/3 pi r cubed, where r is the radius. We can approximate this. We can say, we're going for rough numbers. We can say pi is 3. Perhaps. I think that might be
yeah, that's a reasonable idea. Yeah.
So that'll give us 4, and then 2 times 10 to minus 2 meters cubed, which is, so 2 cubed is 8 times that before is 32 times 10 to minus 6 meters cubed. And then might as well quickly put that into standard form again. 3.2 times 10 to minus 7 meters cubed. now we need to estimate the volume of a car, which we can potentially
That
dubiously
last step,
approximate
Guy, just
the
to
cuboid.
pause for a second, your conversion there.
I see my errors. That should be -5 at the end. Yes.
Okay, so now for a car, let's think about that. So yeah, what did you just say? I'm sorry I interrupted you because
no, it's okay. It's probably a decent idea to approximate it as a cuboid. Any more might be a little bit too much work in this estimation. And we could give it dimensions: length 2 meters, perhaps, width about 1 meter, height 1 meter.
Yeah,
sounds quite reasonable. Giving a volume of 2 meters cubed. And then in terms of number of balls we can fit into a car, a crude way of doing this is finding the volume ratio. I think there'll be an issue with sort of there will be some space in between. So if you're putting lots of balls on top of each other in a structure, I think there will be inevitably some error, some space in between them.
Let's do the easy thing to begin with. Let's do the most straightforward.
Sure, yeah. So then we'll take number of balls. I'll just put that as number. Will be 2 meters cubed over 3.2 times 10 to the minus 5 meters cubed, which we can approximately say it's about, so 2 over 3.2, it's about 2/3, 0.67 times 10 to the 5, or approximately 7 times 10 to the 4, so 70,000.
Yeah. Okay, so that's a great first estimate. And as you said, though, this is a kind of very simplistic estimate. And what we're going to try and do now is think a little bit more about what's going on. So I'm going to hop on to the next thing. Has that changed for you? Yep. Great. And I'm going to put a different picture up for you now. Which is this one. Okay. So, as you said, there are going to be gaps in between these balls because the spheres don't tessellate. There will be air gaps in between them. And you may or may not be familiar with close packing. Is that something you've come across before? You may actually have come across it in your first year at Cambridge.
Admittedly, only at Cambridge.
Indeed. So during your schooling, you might not have come across this. So I would then explain this to you in quite a lot of detail. So when you try and pack spheres together, there's actually quite a well-defined way that they can be packed that is the most efficient way in terms of filling up the space. And there are 2 possible ways that you can describe this in terms of like a crystal structure. One of them is this face-centered cubic structure. So what you're seeing here is 3 different pictures of the same thing, which is what we call the unit cell of that structure. So this is describing the way that the spheres can sit together in the most efficient way. This is just showing the spheres, I guess, in terms of the 3D space. Then the middle picture is a slightly more schematic, I guess, diagram of this unit cell. And then on the right is showing the sections, if you like, of each sphere that fit within that unit cell. And this unit cell is the thing that you would repeat many, many times to build up a crystal structure. And this crystal structure actually is quite common in material science. It's the way that metals are structured and so on. Okay, so it's something that comes up in science quite a lot. So if I give you this picture, and I would recommend you look at this one on the right-hand side, because that's the easiest one to see what's going on. What you can see is that you've got spheres at all of the corners of the cube, which is the repeating unit, and then also, maybe it's easier to see on this central picture, at the center of each face too. Okay. Using this diagram, can you work out for me how much of this cube is filled up with spheres. And I think let's just call this the side of the cube L, okay? Let's give it a general length.
Sure. Right. And are we saying the blue and the red spheres here are the same, sort of same size? And
yeah. Sure. So the blue and the red, sorry, it's just to indicate which ones are sitting in the center of the face of the cube and which ones are on the corners.
Got it. Yeah.
They're all the same size.
Yeah. So very quite simply, volume of the cube will just be L cubed.
Yep.
And now we need the total volume that the spheres are occupying, which I suppose we'll get from the number of spheres in the cube as well as the volume of each sphere.
Yep.
So for the number of spheres in the cube, this is quite challenging. It's taking me back.
So maybe I can give you a hand here, Guy, which is the way this picture on the right-hand side is supposed to show you which part of each of these red and blue spheres is actually sitting within this one unit cell. Yeah. Right.
I see. Okay. So the red ones, of which depicted in each unit cell, there's 6 of them.
Yeah.
And we can see from the picture on the right, it's quite useful actually, that each of those 6 are they're split in half, as in they're shared between, I guess, 2 boxes. They're shared between the 2 unit cells. So NR meaning number of red, we can say is 6 of them, but they only occupy half a cell each, or they're split over 2 cells. So that would be 3 of those per cell. And then the number of the blue ones, there's 1 in each corner, visibly here. So that will give us 8. But we can see that each one is shared over 8 cubes. We can only see 1/8 of the each blue ball in the image on the right.
Yep.
Which gives a total of 1 total blue one per cell, and therefore total number of balls per cube is 4.
Yep.
So now we need is the volume of each sphere, and we need to find that. To get the volume, we need the radius, and to get the radius, we need how it compares to the length of the cube. And I believe, can I draw? I can draw on the image. Very nice.
Yep.
So it looks like all of those are touching.
Yeah, that's
so
correct.
If we have, if we say the radius of each sphere is r, we have that along the diagonal, we have 4 lots of the radius, a blue and then 2 red and then a blue. And that is also equal to the diagonal length of each side of the sphere. So that will be root 2L, just a quick Pythagoras, LL. L squared plus L squared is some other thing squared, which must come out as root 2. So I'll draw that there. So that gives the radius as L root 2 over 4.
Have you lost a factor of 2 there?
Hang
on, take a moment. No, you haven't. Sorry, you haven't.
Okay.
Ignore me. Carry on.
Sure, will do. And therefore the volume of each sphere, I'll just put that in the bottom left here, is 4/3 pi r cubed, L cubed, and then we need root 2 over 4 cubed. So I might just put that as 4 cubed, and then root 2 cubes will be 2 root 2. Continue the working over here, a bit more space. And then the final thing we want is, so that's 1 sphere, and then the volume of 4 spheres over the total volume, which is given up here as L cubed. So the efficiency, I guess we can call it, the amount of space that the spheres are actually occupying is this thing in the bottom left divided by L cubed, so that or cancel, we'll just have a final number, and also times that by 4. So pi 2 over, one of the 4's already cancelled, we've got another 4, so over 12.
So somewhere in here, this step, we've gone a bit wrong, but you've got the right idea here. So
sure,
that's fine. So then, can you figure out roughly what that would be numerically?
I'm not sure I can, sorry.
Oh, okay. So what's the value of pi?
About 3-ish, 3.14, so on.
Yeah. And root 2, do you know that?
Yeah, it's about 1.4, I believe, 1.41.
Yeah. So we're doing I'm not sure I can write this down. You're doing 3.1-ish times by, we'll cancel that out and make that 6 underneath, yeah? Times by 1.4, whoops, divided by 6. Okay. Need that roughly?
Roughly, yeah. 3.1 was about 4, and then over 6, so the answer is about 2/3.
Yeah, it's about 70%, I think, that one.
Cool.
Okay, so that's actually the end of this question, Guy. And you've gone through it pretty quickly, which is great. I do have another question that we could use. However, I'm kind of mindful of the time as well, and that people in the session may have questions for us. So I guess probably it's a good place to stop. And I'm just going to switch my screens over. I'm sorry, I keep looking over there. Right, perfect. So how did that compare to the questions that you were asked in your actual interviews?
Pretty similar, I'd say, on the whole. I remember struggling quite a lot in my actual interview. Clearly not too much, you know, I'm here. And yeah, it compares quite a lot, I'd say, yeah.
Okay, so I think in terms of feedback for the people watching, Guy clearly was a successful applicant, and he made really good progress. Don't blush, Guy. He made good progress with that question. If we had another applicant that maybe wasn't doing so well, there would have been multiple places in that calculation where I might have changed what I was doing slightly, or actually stopped a little bit earlier and moved on to a different question to give the applicant the opportunity to show us what they could do in a different area. So for example, after that initial calculation, I might have asked them to think about the shape of the inside of a car and changed it to a trapezoid rather than a cuboid, so sort of chop the ends off the shape instead of going into the packing density part of the question. I might have helped a bit more with the packing density calculation, or I might actually have given the standard answer and asked them to work out the numerical value and then apply that to their original calculation. So there are multiple different ways that the question can go, depending how the student is getting on, and depending how much time is taken to work through as well. But that was one question, and as I said, there would normally be 2, maybe 3, depending on the length of the interview, on a range of different topics. Okay, I'm sure lots of people have questions already, Amy, is that right?
Yeah, well, people haven't sent in questions yet, so I just want to encourage people to send them in, because, yeah, we have about 15 minutes left of the session, and it's a really kind of amazing opportunity to ask any questions that are specifically around the interview process. So do use the chat function or the Q&A function to send those in, and we will get to those. Yeah, I just want to say thank you, Susan and Guy. That was a really useful example of an interview, and the type of style of questions, and seeing the workings out on screen is a really useful. We're always talking about how students do need to demonstrate and show their workings out, and obviously being able to see that on screen was very useful. Whilst we're waiting for people to send through questions, I guess I can get Susan, you maybe to talk a little bit about how the interview is used in the decision-making process by admissions tutors, and kind of the role it plays in the kind of along the process of the kind of different elements of the application.
Yeah, absolutely. And I should actually reinforce what Amy just said, was Guy was very, very good there at telling me what he was doing throughout, as well as writing it down, but actually verbally saying. So I knew exactly where he was going, and that was really helpful to me as an interviewer as well, because I knew where I needed to intervene or not, as the case may be, and help him. So within the application process, we receive all of the paper materials for our applicants after the October deadline, and we assess those, and that will include information about your students' academic records, personal statement, which I mentioned, references from the school or college. There'll be various other pieces of information that Cambridge collects as well, and we look at all of that information together, along with, if there's an admissions assessment, in a specific Cambridge admissions assessment in the subject that your students applied for, we'll look at the score in that as well, and we take all of that information together. I will discuss it with the relevant subject specialists here at Cambridge, and we will come to a decision about whether or not to actually ask your student to participate in our interview process. And the interview process is, I guess, the final step in the assessment. We interview around 70-ish%, 75% of the people that apply to us, and we interview people who have a realistic chance of being made an offer of a place. So that final step is a very important one, but it's not the be all and end all. It does give us a chance to interact with the student. As you can see, it's interacting with Guy quite a lot there. That's quite important because our teaching processes here in Cambridge are like that. We have a special kind of teaching process that you only see at a few universities in the UK, which we call supervisions. Oxford have them as well and call them tutorials. It's effectively the same thing, but the students will sit in 2s or 3s once a week and discuss problem solving, material from lectures, all of those sorts of things with an academic staff member. And it's a very interactive process. So that's partly what the interview is trying to mimic. As I said earlier, we're also trying to test for problem solving and thinking and kind of logical approaches to questions. And it gives us additional information as well as all of the other information we have on the paper form. Once the interviews are finished, we will then go back. We will look at how the applicant's done in the interviews, but we will also take into account all of that paper information that we looked at beforehand, and any test scores, for example, that we have, put all of the information together, and then come to our final decision.
That's really helpful. Thank you, Susan. Some questions have started to come in, so
Good.
we will move on to those. Tanushka has asked, would you provide a formula if the student asked, and would you expect to know most of the formulae that would be used? Would it be held against the student for asking for a formula?
So absolutely, we provide information if a student's not sure. I think if it was, so for example, the